Let's look at the moment generating function of a sum of variables. Recall that the moment generating function is m of t. It's the expected value of e to the xt. Let x1, x2, x3, ... and x sub n be independent random variables with moment generating functions m sub 1 of t, m sub 2 of t, m sub 3 of t, ... and m sub n of t, respectively. Find the moment generating function m sub y of t for y equals x1 plus x2 plus x3 plus ... plus x sub n. Okay, again, y is the sum x1 plus x2 plus ... m sub y of t, the moment generating function for y, is the expected value of e to the yt. So it's the expected value of e to the x1 plus x2 plus x3 ... times t. We can distribute the t and get the expected value of e to the x1t plus x2t plus x3t plus ... plus x sub nt. And because of the law of exponents, we can break that up. That's the expected value of e to the x1t times e to the x2t times ... But because the variables are independent, we can separate that expected value. The expected value of e to the x1t times e to the x2t, etc., is going to be the expected value of e to the x1t times the expected value of e to the x2t, etc. But that is just the moment generating function for x1. That's m1 of t times m2 of t times m3 of t ... times m sub n of t. So in other words, m sub y of t is m sub 1 of t times m sub 2 of t times m sub 3 of t ... times m sub n of t. In other words, the moment generating function of the sum is the product of the moment generating functions. This result is handy and can be used to solve problems on the sample Society of Actuaries exam P, like this next problem. So this is from the 2015 SOA Sample Exam P, problem 58. Company insures homes in 3 cities, J, K, and L. Since sufficient distance separates the cities, it is reasonable to assume that the losses occurring in these cities are mutually independent. The moment generating functions for the loss distributions of the cities are m sub j of t equals 1 minus 2t to the negative 3, m sub k of t equals 1 minus 2t to the negative 2.5, and m sub l of t equals 1 minus 2t to the negative 4.5. Let x represent the combined losses from the 3 cities. Calculate the expected value of x cubed. We saw in the previous problem that the moment generating function for y equals x1 plus x2 plus x3 plus ... is m sub y of t equals m sub 1 of t times m sub 2 of t times m sub 3 of t, etc. Thus, the moment generating function for x equals j plus k plus l is m sub x of t equals m sub j of t times m sub k of t times m sub l of t, which is 1 minus 2t to the negative 3 times 1 minus 2t to the negative 2.5 times 1 minus 2t to the negative 4.5, which is 1 minus 2t to the negative 10. We were asked to calculate the expected value of x cubed. Recall that the expected value of x cubed is the third moment, m triple prime of 0. m sub x of t is 1 minus 2t to the negative 10. We need to find the third derivative. So m sub x prime of t will be negative 10, 1 minus 2t to the negative 11 times negative 2. And here's where that comes from. So again, this negative 10, when we take the derivative, comes out front. And then we also multiply. That's where that explains this negative 10. And as for where this negative 2 comes from, that's just the derivative of the stuff inside parentheses. That's just going to be minus 2. So when we simplify that, we get 20, 1 minus 2t to the negative 11. Take the derivative of that. And again, to take the derivative of that, you pull the negative 11 out front. So you'd end up with negative 220 times 1 minus 2t to the negative 12 times negative 2. And again, this negative 2 comes from the fact that the derivative of the inside is negative 2. And that simplifies to 440, 1 minus 2t to the negative 12. Oh, but we're not done yet. One more derivative. M triple prime of t is going to be negative 12 times 440, 1 minus 2t to the negative 13 times negative 2, which is 10,560. 1 minus 2t to the negative 13. And when we plug in 0, m triple prime of 0 is 10,560 times 1 to the negative 13th, which is 10,560. Thus, the expected value is 10,560, which is answer E.